going to have another opportunity for close to an hour of discussion. It seems that we have gotten very good at discussing and having a lot to talk about, so I'm glad that we have that time available. Our next speaker is going to be Craig Benson. As we know, in these closure processes, the caps and liners are issues of great importance and also discussion, and Craig is going to be talking about his experiences understanding the performance of them.
Working? Yeah, good. Pleasure to be here, talk about something that's dear to my heart and something we put a lot of energy in over the last 20 years, trying to understand the performance, being able to predict the performance of barrier systems, covers and liners used for waste containment facilities at the near surface, contrasting some of the other discussions for deep disposal. Here we're talking about really landfill type of facilities. So we look at schematically, just to put it in context, everything's near the surface. So we've got a final cover system that's got barriers in it, primarily intended to limit the entry of liquids into the waste, which might generate leachate and then migrate down to groundwater, and then some barrier system in the bottom as well that's meant to be both a hydraulic barrier to prevent leakage and also a transport barrier to minimize contaminant transport to some acceptable level. The use of liners depends a lot on the setting in which the facility's operative. Some sites, depending on the regulatory environment, won't have a liner, but certainly throughout the DOE complex and D&D activities where CERCLA is involved, liners are very common. For example, at Fernald, Portsmouth, Paducah are all building large line disposal facilities as part of their closure process because they are dealing with mixed waste, which are both regulated through 435.1 and also through CERCLA ARARs. And so they are both have a cover system and a liner system as well. So I'm going to talk about both of those because they're relevant to a number of facilities in the DOE complex. Ultimately, our goal is to protect health and human safety. So these systems, we ought to be not only predicting how they work, but we ought to be evaluating how they work to make sure that they're achieving that goal, making sure perhaps that we're keeping this groundwater offsite at some acceptable level. If we look at final cover systems, just to give you a little more context, because I'm going to talk about different types in my presentation, we could categorize covers into two different types, and there's been a number of folks who've talked about this already, but so-called conventional covers that use some type of resistive elements within the cover system, essentially block the flow of liquid. The most common are a combination of polymeric materials and earthen materials, a composite barrier as we call them, typically made out of polyethylene combined with compacted clay, or polyethylene combined with a geosynthetic clay liner, which is a factory manufactured mineral barrier that comes in a roll. And then some other layers. For example, we might have a drainage layer, we'll talk a little bit about those, and then an erosion layer on the surface and the waste at the bottom. But a conventional cover systems use some type of resistive element to essentially block the flow of water. Very common in eastern parts of the country where there's a lot of water to manage. On the other hand, in more arid areas, we might use other methods to manage water at the near surface, so-called water balance or store and release covers, which are thick engineered layers of soil where we manage all the water essentially through storage within the cover profile, storing it during wetter periods, and then releasing it during drier periods through both surface evaporation and transpiration by plants. You see these roots going down through the profile, essentially acting as pumps to extract the stored water and release it back to the atmosphere. So we could use really very different types of technologies for covers. We could essentially block the flow of water, which is very common in humid climates, or we could essentially store it and release it through a water balance principle in more arid climates. And we'll look at some information on both of these. Sometimes we do both. If you really want the super duper cover. This is the UMTRA disposal cell cover in Monticello, Utah, DOE facility, which has a store and release cover at the top, essentially about 2 meters of store and release material with a biota barrier in the middle or towards the bottom. This is all meant to store and release water. Actually works very effectively on its own, but also has a barrier at the bottom here a composite barrier of clay and then a geomembrane traditional resistive barrier, essentially putting both together. So sometimes you'll see both. I think the DOE industry is the only one where you'll see that, because it's an expensive proposition. Lining systems look a lot like the conventional cover systems, the barriers we use. You might see them in varying grading of materials. We might have a simple clay liner being used for some MSW facilities, but certainly not very common in a DOE complex. More common would be a composite barrier, much like the resistive barrier in the cover, conventional cover, a polymeric material combined with a clay barrier. And perhaps more commonly what you'll see at the facilities that are taking mixed waste through circular type of activities. For example, like at Fernald, we'd have a double composite barrier where we'd actually have two composite liners with an intermediate drainage layer between to essentially collect any liquid that makes its way through the first liner. And these are really effective systems. They're very effective at restricting both the flow of liquid and the transport of contaminants. We have something that's very good at knocking out the advection, essentially the flow, and we have a nice adsorptive barrier for, at least for metals and the like, in these mineral layers made out of clay. So when we talk about these type of barrier systems, we want to predict their performance for a performance assessment. There's probably, in my mind, there's three fundamental questions that we ought to be asking, and the answer to these questions ought to then be reflected in our confidence in our performance assessment and our uncertainty in it. You know, first of all, and some of these, I listened to Dave Esch's talk yesterday, which I really liked, and these reflect some of the thoughts he had. I actually went back and worked on my presentation last night based on what he had to say. You know, do the models really reflect the physical, biological, and chemical processes that exist in the field? Are they reasonably realistic? Realizing that they are models, they'll always be an abstraction, but are they capturing the key processes? If we have the physical, chemical, biological processes down, can we parameterize them? That's another big issue. We may have a really great model that runs on a supercomputer, but in the end, most models, their predictive capability depends on the input you put into them. And I think this is perhaps one of the biggest issues that we have to deal with is parameterization, not model capabilities themselves. And then finally, can we really simulate how the properties and processes may change over time? It's really three different elements. And we'll talk about those as we go through. If we look at covers, essentially covers and liners, I just broke down essentially my thoughts on the key processes in each of these elements and our state of knowledge with regard to prediction. If we look in conventional covers, we have to deal with unsaturated flow and root water uptake in the earthen layers that are above the barrier system, above the polymeric materials. We have a high level of capability in the unsaturated flow part. Our vegetation models tend to be, they're just okay. Jody Waugh's not here yet. He's an ecologist I work with who does work with LM, and he would argue that our vegetation models are horrible. And so we're somewhere on two ends of the spectrum on that. But I think this is an area where we need to work on that particular aspect. But again, a lot of this, our abilities come down to parameterization. Can we put input into the models that gives us a reasonable output? We look at below the top part of a conventional cover. We get down to the geomembrane and the clay part. That's where our predictive capabilities really become dicey, and I would argue are okay at best. Typically what we do, we tend to have some defects in the polymeric materials, and there's flow through those defects and then down through the underlying earthen materials. And what we normally do is model the top part with an unsaturated flow model, take the output for that and put it into analytical solutions for the barrier system, and that's okay at best. This is an area where we really need to put more energy into. We look at water balance covers, so-called store and release, where we're storing the water and then releasing it via the atmosphere. I would argue that our models for those systems have a higher level of capability than our combined models for conventional covers. They're really they're very similar to what's going on in the surface here. We have a high level of capability, again, in the unsaturated flow components. Our vegetation, again, is the weaker part. and parameterization, again, it really being a key part. If we look at liners, we have a leachate collection system and then a barrier system underneath that. I think we have a high level of capability of predicting the flow processes and leachate collection systems, but perhaps one of the big issues is the long-term geochemical impacts. Simulating the geochemistry, which is going to go on over decades within that collection system, how it's going to affect the pores within the collection system and its ability to conduct and collect flow. In composite liners, we really have a high level of sophistication for simulating the flow and transport of contaminants we see in other types of containment facilities, primarily municipal solid waste and hazardous solid waste facilities, volatile organic compounds, metals, things that we would see certainly in mixed waste. We really ought to be trying to extend these models to LLW landfills, and I think we can do that fairly effectively. Again, what we find for these types, for composite liner models, again, the parameterization is the key, but they seem to be easier to parameterize than our cover models. The models for liner systems, I'll talk about those just for a few minutes because I'm going to primarily focus on covers. What we found is that we model these in a couple of different ways. If we're looking at inorganic compounds, which tend to not partition into the polymeric materials to a significant degree, we need to look at essentially defects that exist in our plastic component of the liner, flow and transport through those defects, the holes, and then transport through the underlying clay barrier. If we're looking at VOCs, other types of organic compounds that will partition into the polymeric plastic, we can use diffusion-based models, pure diffusion models, and they tend to be very, very effective. We've recently had the luxury of conducting some large prototype experiments and analyzing a suite of field data with regard to VOC transport through composite barrier systems. I don't have any graphs to show you today. I talked to my colleagues about this, and they were a little reluctant to present it completely. It's kind of hot off the presses, and we're finishing this up right now. But one of the things that we found is that our models that we have for composite liners are pretty darn good. We can measure laboratory measured inputs, put those into those models, and they will predict what we observe in our prototype scale experiments and in the field pretty well. They do a pretty good job. They're pretty simple. They use essentially linear partitioning and laboratory measured diffusion coefficients, and yet we get, despite their simplicity, we get good predictions from these models. They are simple in terms of their management of adsorption and essentially, I guess I put it simplistically, they just manage the solid-liquid phase interactions pretty simply. If we really wanted to make these models better, we would build in some geochemical reactive transport models, and we haven't done that yet. Some disadvantages, none of the models have been validated for radionuclides. So we looked at VOCs, we looked at traditional metals that we would see in other types of waste streams, but not for radionuclides. I mentioned already, none of them include reactive transport based on fundamental geochemical principles. So they're not reactive transport codes, they just rely on simple isotherms and linear partitioning. We really have, and I think this is an issue, we really have no long-term data on the transport properties of liners. One of the things about covers is they're at the surface. We can usually convince people to let us dig them up periodically. Liners are underneath the waste, and even if we could get at them, most of the time folks are reluctant to dig them up given the potential impacts of having to remove and perhaps relocate waste. One of the things that we do have, though, is that we do have analogs of similar systems. Jim Hendry's group at Saskatchewan has done some really neat work on aquatards up in Canada and looking at chloride transport through aquatards, and they provide a nice analog to our lining systems. They tend to be clay-based materials. They tend to be under confinement, so they're under higher levels of stress, and they tend to be covered with things which keep them from going through wetting and drying and freezing and thawing cycles. And those data sets, which provide evidence for essentially 1,000 years or more, would give us a good indication that our barrier systems that we build for containment facilities, for liners in containment facilities, have the potential to function for a very long period of time. I say very long period of time because I'm always reluctant to put a number on that. The geosynthetic elements on that, the clay parts, I think we have good analogs for. The geosynthetic parts, the polymeric materials, we have less evidence in that regard. Although my sense is, given that these materials are buried and are under high stress, they're in an environment which is going to reduce the rate at which they degrade over time compared to the way they would degrade in a cover. I think we need to learn more about these materials, but I have a sense that they're going to last a lot longer than perhaps we give them credit for. Talk about cover systems a little bit. I'm going to talk about the earthen cover systems, then talk about the conventional systems. We talk about modeling earthen cover systems, and put in the partial differential equation right here after the break. Don't want to put anybody to sleep, but this is the fundamental equation that we use to describe the management of water in these systems, the storage and release of water to the atmosphere. And if we parameterize this properly with the hydraulic conductivity components and the relationships between water content and potential in the pore water, in fact, we can get pretty good predictions from these models. These models are available commercially and are used pretty widely. UNSAT-H model that comes out of essentially DOE work, model VADOS W, which comes out of essentially work in the Canadian and Australian mining industry, and Hydrus, which came largely out of work out of the USDA Salinity Lab. They all do essentially the same thing. I'm not monogamous with a particular model. I can't remember who talked about that yesterday. These all do the same thing. They have different little bells and whistles for them. But they all do a very good job if we parameterize them properly, and that's what we'll see. One of the weaknesses of all these, though, they treat the plants very simplistically. We have a root water uptake term and some very simple vegetation terms that we put in to characterize the vegetation. And that's an area that we need to improve on. And none of the models really have anything built in to simulate temporal changes in properties over time. That's something the user has to get data and then run it for a period of time and then put in a new parameter set and rerun it. If we look at our predictive capabilities for these type of models, this is for a site in Northern California, east of San Francisco, kind of in the pass there between Livermore and Tracy, California, for a store and release or water balance type cover. And this is the drainage out the bottom or percolation into the waste. And the black line is the field data. The blue line is a prediction with the model using our as-built properties. And then the red line is the prediction from the model using properties that we measured later when we went back actually and dug up the cover and characterized the properties. And you can see our as-built performance, we actually are unconservative. But if we actually know what those properties are more reliably, we get a pretty good answer, all right? So if we can parameterize it well, we can get a reliable answer. And so that's the rub. Can we parameterize it well? I'll give you another example. This is a monolithic cover, store and release type of design near Monterey, California. This site was designed to transmit less than 3 millimeters per year of water into the underlying waste. And that design was done with as-built properties, essentially traditional design process. And again, when you're designing an actual facility and looking forward, you don't have the luxury of knowing what the properties are going to be. You have what you measured during design. And the prediction, of course, here, this is 3 millimeters. Here was our design, and this is the type of data we got out of our monitoring system. I'll just focus on a little bit of this. These are cumulative quantities versus time, and we'll look at this one, cumulative percolation, as the key driver right here. That's the red line here, cumulative percolation over time. And again, 3 millimeters per year, all right, was our design standard. And you can see after about 4 years, we're at about 200. So we were off in this particular case because our input that we put into it to parameterize the model was biased, the design information. So parameterization is going to be important. I'll come back to that a little bit more. As I already indicated, in cover systems with composite barriers, things get more complicated. We have this upper part, which is like a store and release cover. We have soils, we have plants, and water flows in, it gets stored and released. But we also have a barrier system below, and perhaps even a drainage layer in here. As I mentioned, we typically take make predictions of flow out the bottom of these systems and then put them into analytical models for flow in the drainage layer and then flow through a defect and then down below. And our analytical or anecdotal comparisons that we've done indicate this combination of analytical and numerical methods is just okay, and a lot of times isn't conservative. This is something that we need to work on if we're going to use these barrier systems more. We need to develop better models for that. Well, I talked about parameterization being important, and I think as we gather data, we learn about maybe we would do things differently. And I love this slide because this is a real paradigm. These are real advertisements from the 50s. At the time, we had a certain perspective, and we gathered data, and that changed our perspective. It allowed us to improve what we do things better. I like this one. They're happy because they eat lard. Who would ever think of that today? So one of the things that we need to do, and Dave Esch talked about this as well yesterday, is to collect data about how these systems function and how the properties that we are actually being realized in service, how they compare to what we see during design. One of the things that we've done in the last several years is conduct a study to do exactly that for cover systems. We had a large cover study called ACAP, the Alternative Cover Assessment Program, where we actually monitored covers throughout the United States at a variety of different field sites, actually 28 different field sites throughout the U.S. And we were interested in how they performed and whether we could predict the performance. And when we were done, one of the things we realized we really needed to understand our in-service properties of these cover materials better. And so we went back and spent 2 years essentially digging them up and characterizing the in-service condition of the cover materials. We ran field tests like you can see here. This is actually that site in the pass between Livermore and Tracy, California. If you look in the back here, right up in the top, it's cropped off. You'll see all those windmills. If you've been through that pass, you know it's a big wind farm area. But running a series of large field tests to characterize in situ hydraulic properties. This is just the different sites where we've done these exhumations at, and we've collected a fairly large database now on the properties of in-service cover materials. And all the starred sites are where we actually were able to do these exhumations to study the properties. We looked at the development of structure in the earthen materials at these sites. We tend to think of these, we put them in a homogeneous, uniform format, or essentially structure when we build it, and it changes over time. As the cover interacts with the atmosphere and the biota, lots of structure develops within the cover profile. This is actually the cover at the Monticello disposal facility. There's some markings on here for geomorphological mapping exercise. I think this is a good example of how things are different in service than they are in our plan or in our intentions. This is a sample of a clay radon barrier from the Monticello facility, intended essentially to be an intact homogeneous clay barrier. This is 2 meters below ground surface, all right? Meant to essentially serve as both a radon barrier up and a hydraulic barrier down. And you can see that this is not an intact material. We've had roots make their way down into the radon barrier, fracture it, make it much more permeable both to gas up and to flow down. So understanding these type of processes is important. And we also sampled a lot of the geosynthetic materials as well, not only the earthen materials, but collected samples of the geosynthetic materials, the earthen materials, brought them back to the lab and did laboratory tests to complement our field work. And I'll just talk for a couple minutes, because I've got to finish up here, about done. But some of the things that we've observed, I'm just going to show a couple examples that are, I think are important. We look at earthen barriers, the saturated conductivity of these materials. This graph shows you the in-service saturated conductivity of different types of barrier materials, either from so-called water balance or store and release covers or composite covers, clay covers, versus what we expected when we built it. And this one-to-one line would correspond to in-service being equal to as built, all right? So it behaves like we expected. None of the data are on the one-to-one line. Everything changed. Every site changed. The hydraulic conductivity, here's a 10-to-1 line, increased by at least a factor of 10 within several years, all right? In some cases, over a factor of 1,000. And what you see is if you don't consider these 2 points, most of this data, there's almost no relationship with the initial conductivity. There's no real trend with the as-built values. Most of the data seem to be coalescing into a band here between about 10 to the minus 7 meters per second and about 5 times 10 to the minus 6 meters per second. And the average is about 5.5 times 10 to the minus 7 meters per second. And what we see is that range is about a factor of 50 over all the different sites, whereas when we started, the range was over 4 orders of magnitude for the different sites. So things are becoming more similar over time. They all change and they become more similar over time. Nature has this way of taking things that are, I think somebody talked about this yesterday, you know, the farther you make them different from the natural system, the more nature will push back and tend to change them. Here's just another example. These are just synthetic clay liners. These materials, when they're as-built for design, we will typically assume that they have a hydraulic conductivity less than 3 times 10 to the minus 11 meters per second, down here in this gray band. We have things all over the place, all over the map. What's interesting, one of our most severe sites in the Mojave Desert, everything's great at that site. You know, it's in the Mojave Desert, and we have ones in Wisconsin where you would think it's wet and things are buried deep and it would just be pristine, and they're some of the worst. So these materials change as well. It depends a lot on the placement conditions and the different aspects of design. We found whether they tend to remain much the same or change very differently. Things that we didn't know before and we wouldn't have known if we hadn't excavated and studied these materials. If I could summarize what we learned from that, all of the saturated and unsaturated hydraulic properties of cover soils have changed in all cases, and they become increasingly similar over time. The geosynthetic clay liners, as we talked about, they underwent chemical changes that induced hydraulic changes in hydraulic properties, and that depended a lot on the placement condition. They could have very good properties or very permeable properties depending on placement conditions. I didn't show any data on this, but the geomembranes that we looked at really didn't have any degradation in properties, but were able to monitor their loss of antioxidants, which is essentially a chemical compound that's put in the polymer to prevent it from oxidizing, and the rates at which they would depleted were pretty consistent with what is predicted based on laboratory experiments on theory. And so that allows us then to go back and calculate how long is it going to take for the antioxidant to be depleted, and then at that point the degradation processes will accelerate potentially. And if you do that calculation, you get a lifespan on the order of about 150 to 150 years in a cover system. Probably very different in a liner, but in a cover about 50 to 150 years in a cover system. That means if you're going to use those in a cover and rely on them, you're probably going to have to replace them over time. And there's been a lot of discussion about there are value to these materials in looking at evolutionary covers, where perhaps the cover design evolves over time, and we don't necessarily build a cover at the very beginning to last for 1,000 years, but perhaps we build a series of covers that have different types of materials in them that'll actually give us better performance and lower our long-term costs associated with it. Drainage layers, I didn't show any data on that, but we found that they had modest reductions, and you could count on about a 6-fold reduction about every decade in those materials. The big issue, though, is we've got data from about 10 years, and we've got these very long-lived contaminants that we've got to manage. So when we take our data set, here's our as-built, here's what we know now, this is our exhumations, and then where do we go? Where's it going to go from here? My sense is a lot of the changes have occurred. We see a lot of changes very early on. Things are going to settle out, but they're certainly not going to be the same as what we saw here at a decade. And I think this is where we need to do more with analogs to look at where things are likely to go, to look at natural analogs. We haven't done as much of that as I'd like to. There has been some really nice work done in DOE for site-specific applications at Hanford, and some of the work done in UMTRA as well, which I think to do more of that type of analog studies is going to be helpful in terms of predicting long-term performance. Just some concluding remarks. I think our predictive capabilities, like a lot of academic things, we always say the same thing, it all depends, right? Typical academic answer. Yeah, they work in some cases. We can get reliable predictions in some cases. Other cases, we need more effort put into the models. You know, we're good at store and release covers. Conventional covers, we're just okay. We are very good at modeling VOC transport through barrier systems, but we have no data on radionuclide transport. So we need to continue to work on these models as we go forward. I think properties of liners, although we have very little data on long-term properties of liners, they're likely to be much more stable than properties in covers. They're buried, they're under high stress conditions which tend to essentially close pores and minimize defects. The analogs that we have from similar systems in aquatards suggest that they will have a long life. The geosynthetic materials need more study in terms of predicting their lifespan. None of our models that we use for these systems, whether they're covers or liners, allow us to simulate these changes over time, and it would be good to be able to build that into our models. We essentially have to do it ad hoc right now. Our field data have shown that, at least in cover systems, things change. We should be accounting for those changes in our cover models. They change fairly quickly, and they become increasingly similar over time. There seems to be a band almost into which most of the hydraulic properties are falling. We see changes in our geosynthetic materials as well. Some are more predictable than others. The geomembranes and drainage layers tend to be much more predictable than the geosynthetic clay liners. But most of these that we can incorporate into our models fairly readily. I think just a couple of points to end with is, you know, we wouldn't have learned a lot of these things without collecting data. And this is one of the things that Dave talked about yesterday, is to do smart monitoring, is to monitor elements of a containment system and see whether they're really functioning as intended. Monitor for function as opposed to monitoring for compliance. They're really two different things. We have to monitor for compliance from a legal perspective and perhaps from a stakeholder perspective as well. But we ought to be monitoring for function as well to see if the elements that we're building really perform the way we expect them. And if they aren't, then we ought to be changing our designs. In fact, there may be cost savings that we could accrue through doing that. We can develop better models, create better materials, better designs through that type of data. And if we don't collect the data, you'll never know. So I'll leave it at that. We're going to have questions at the end, as I believe. So, all right, great.